Welcome again to a portfolio theory video. I'd like to start by quickly reviewing the capital market line, the CML. It's an equilibrium relationship between expected portfolio returns and standard deviation of returns of a portfolio. For efficient portfolios only, efficient portfolios have no unique risk. And here we've got expected return on the portfolio on the vertical axis, standard deviation of return of the portfolio on the horizontal axis. This, of course, allows risk-free borrowing and lending, but it assumes there's a single risk-free rate at which we borrow and lend. I've already talked about that in another video being very unrealistic. I'm showing you this video because you'll probably see it again if you go to graduate school in finance. And so here is the risky efficient set. When we allow the possibility of risk-free borrowing and lending, then we see that there's just one portfolio M, that investors would choose to invest in. And the CML is a straight line, and it looks like this. The formula is presented here. Notice the slope is rise over run. If we run from here to the market standard deviation, that's our run, the rise associated with that is to go from risk-free rate to expected return on the market. So that's what we have here. And then, of course, the X variable, if you will, is sigma portfolio. Okay. Next, I want to review securities market line. It shows the equilibrium relationship between expected return on any security and the beta of that security for all securities. So here's expected return on security I, here's beta of security I. It's a straight line. The vertical intercept is the risk-free rate. And this right here would be the market portfolio, just to show something. And there's the expected return on the market. There's the beta of the market. Of course, the beta is the covariance of the securities return with the market's return. In this case, the covariance of the market's return with the market's return divided by the variance of the market's return. So, of course, that's the same as variance of the market divided by variance of the market, or 1. So, in other words, the beta of the market is 1. And this is for single securities. This also holds for portfolios. Here I'm reminding you the beta of a portfolio is a simple weighted average of the betas of the stocks that constitute the portfolio. And here I'm reminding you the fact that the expected return for a portfolio is a simple weighted average of the expected returns of the securities that constitute the portfolio. Therefore, the expected return on a portfolio is the risk-free rate plus the portfolio beta multiplied by the excess return on the market. It's the expected market return minus the risk-free rate. Okay, and here's a little chart that distinguishes an expected return that we might have from an equilibrium expected return like might come from the securities market line. Oh, by the way, remember that the securities market line is just the graphical depiction of the capital asset pricing model. Okay, so down here we have a relationship expected return on stock I on the vertical axis, beta I on the horizontal axis. And here we make some assumptions. Let's assume that the risk-free rate is 4%, that a stock I has a beta of 1.5, and the expected return on the market 12%. And we expect the return on stock I to be 14%. That's our expectation, distinct from the prediction or the equilibrium expected return given the SML. So here we go in our analysis. There is a beta of 1.5, and we see that a beta of 1.5, if you do the algebra right here, I'm showing you this term alpha. So let me just back up a second. Alpha is defined as the expected return on the security minus the equilibrium expected return on the security, like the return predicted by the capital asset pricing model. Alpha is a measure of mispricing. And this term right here is your own expectation for the stock's return over some upcoming period. You may have got that information by looking at one analyst or averaging information presented by multiple analysts, okay? And in this example with these assumptions, if the stock had a beta of 1.5, we see that the equilibrium expected return would be 16%. So if you plug these values in to the formula for the capital asset pricing model, then you'd get 16%. So here when we're showing the alpha as being the difference between the expected return on stock I and the equilibrium expected return, down here the equilibrium expected return is the SML or the CAPM, risk-free rate plus expected excess return on the market portfolio times beta. And if you plug in 4% here and the beta of 1.5 and then 12% minus 4%, so you get 8% times 1.5 is 12% plus the risk-free rate of 4% means 16%. So a beta of 1.5 would be associated with an equilibrium expected return of 16%. But our expected return, for whatever reason, is 14%. That's just our opinion. And so at a beta of 1.5, we see this dot here represents our expectation. The ordered pair here, abscissa and ordinate, 1.5, and then 14%. It'll be right here between these two. And that vertical distance right there is alpha, and it's minus 2%. Since the security is earning, since we think it'll earn less than it should, then we think the security is overpriced or under-returned, if you will. Okay? So down here we just plug in our own expected return, 14%. We subtract out the equilibrium expected return, in this case the CAPM, which ends up being 16%. We see that alpha is equal to minus 2%, therefore the security is overpriced. Here's just a little chart. Whenever the dot at the beta level is above the SML, the security is underpriced, you might think over-returned, or as in the example we just had up here, where the dot was below the SML, as is here the case, the security is overpriced or under-returned. Okay? So both the CML and the SML are equilibrium relationships. Now let's turn our attention to a disequilibrium framework. The characteristic line is a disequilibrium framework. And let's start here by talking about expectations. We just did alpha is the expected return on I minus the equilibrium expected return. And we're just doing some algebraic manipulation here. Here we're distributing the minus sign. And here I'm moving this to the left-hand side. And then I'm just flipping the left-hand side and the right-hand side. So we have the expected value of the return on security I minus the risk-free rate. The expected value of the return on security I minus the risk-free rate is equal to the mispricing alpha I plus beta times the excess return or expected excess return on the market portfolio, which is the expected return on the market minus the risk-free rate. Okay? Now, let's, instead of talking about expectations, let's talk about what actually may have occurred or what actually occurs. So now we're talking about actual. So instead of having an expectations operator, we just have the return, R sub I minus the risk-free rate, equals alpha I, the mispricing, plus the beta, times the excess return on the market, plus this epsilon sub I, a measure of mispricing. It's the vertical distance from the characteristic line that actually came to be. It's not depicted here, but maybe it's there or maybe it's there, and that vertical distance is the epsilon. Okay, now let's look at this characteristic line. First of all, a characteristic line is for one security, and the slope of the characteristic line is the beta of the stock. So here we see on the vertical axis we have the excess return on stock I, which is the return on stock I minus the risk-free rate, and on the horizontal axis we have the excess return on the market, which is the market return minus the risk-free rate, and of course the excess return on stock I is since the return that we expected was 14%, it would be 14 minus 4 or 10%. And the excess return on the market would be 12% minus 4% or 8%. So that's where the 10% and the 8% come from. Notice, very importantly, that the vertical intercept of the characteristic line is the alpha, minus 2%. Earlier here it was calculated as 14% minus 16% or minus 2%. So the vertical intercept of the characteristic line is alpha. Now, the characteristic line again is for one security, and this is one security and my personal expected return of 14%. So when you create a characteristic line for a stock, it's your opinion. It's your opinion because it's based upon your expected return on the stock. And then the actual is the R sub I, what actually happens. Okay? So now let's get to the diversification. We're taking the actual from above. Up here we had the actual equation right here. I'm just repeating that equation right here. And now we're going to take the variance of both sides of that equation. Okay, the variance of both sides of that equation. We will note that the variance of a variable minus a constant is just the variance of the variable. In this example, risk-free rate, alpha, and beta are all constants. So, subtracting a constant risk-free rate from a variable R sub I really doesn't affect variance at all. It does not affect it at all. In this analysis, R sub I, R sub M, and epsilon R sub I are variables. Okay, so this is just the variance of the return on stock I. The risk-free rate doesn't affect anything. Over here we have the sum of three terms. The first term is a constant. Constants don't have a variance, so there's a zero that's not even showing there. Then we've got a constant multiplied by a random variable minus a constant. We already know that the variance of a random variable minus a constant is just the variance of the random variable, but if we had, in this case, we have another constant, beta sub I, multiplied by the variable, so the variance of that term is beta sub I squared times the variance of the return on the market. And then we have this epsilon term here, and so that is a variable. So we just have the variance of epsilon for the return on stock I. Now, we're left with two variables here. We normally expect to see a lot of covariance terms, or in this case, a covariance term, but this assumes that the covariance between the variable return on the market and the variable epsilon R sub I is 0. Now this same relationship here holds for portfolios. So now we have the variance of the return on the portfolio equals the square of the portfolio beta times the variance of the return on the market plus the variance of the portfolio's error term. And we note that the portfolio beta square is just, well, the beta of the portfolio is a simple weighted average of the betas of the stocks that constitute the portfolio, and then we square it. And so the variance of, and also the variance of the epsilon, the error term for the portfolio, is just the sum of the squared weights times the variance of the residual for each individual stock. Notice we don't see any covariance terms here, okay? We don't see any covariance terms here because we assume that the correlation between two securities error terms is 0. Otherwise, we would have covariance terms up here. And so this right here is the variance of the portfolio's error term. So now we're left with a comfortable equation. This is the total risk of the portfolio. This is the market risk. And then this is the unique risk. And here's a familiar table, a familiar diagram. We have risk on the vertical axis and number of securities in a portfolio on the horizontal axis. Market risk, we know, averages, and total risk falls. And here I'm showing 5 securities in a portfolio, and the distance from here to here is the total unique risk for 5 securities, and here's 12 securities, and the distance from right here to the total risk line is the unique risk for 12 securities, and total risk is falling. And here this makes clear that the reason total risk falls is because as portfolio size gets larger in terms of number of securities in the portfolio, total risk falls. Now, we want to prove that. We want to prove that unique risk falls as the number of names or number of securities in a portfolio increases. Okay? So here, just some background information. Beta portfolio squared times the variance of the market return is the market risk. This term changes as portfolio beta changes. So when securities are added to the portfolio's market risk averages out. Okay? It's heading toward 1, if we're efficiently diversifying or randomly diversifying, our portfolio betas are heading toward 1, unless we intend to have it not head toward 1 and therefore just not randomly choose stocks, but are very specific in the stocks we choose to add to our portfolio. Now here we have the variance of the portfolio's error term. This term decreases as securities are added to a portfolio, hence total risk also decreases. This is what we want to prove that this is a true statement. So here we have the variance of the portfolio's error term being the sum of the weight in each stock's error term variance squared times the error term variance. And again, there's no covariance terms here for reasons explained a couple moments ago. Now, so this is our familiar, this again, just so you're clear, this is the variance, the portfolio's error term, and it's decomposed this way into the variances of the error terms for the individual securities, with no covariant terms, okay? And this is a familiar formula. We've seen this before in our earlier studies of portfolio theory. Now let's assume equal amounts are invested in each security. So if there are n securities, we will have 1 over n invested in each security. So our WIs are all 1 over n, or it's a constant. So I could pool 1 over n squared to the left of the summation in determining the portfolio error variance, okay? But what I'm going to do is remember this is 1 over n squared, it's the same as 1 over n times 1 over n. I'm going to pull one of the 1 over n's to the left of the summation sign. I'm going to leave the other 1 over n there and just divide sigma square epsilon r sub I by n. Now look at what's showing here in this red oval. We are adding something and dividing by n. The thing we're adding is this. Well, whenever we sum something and divide by n, we get an average or an expected value. So we're summing this and dividing by n, so we get average unique risk. So this term right here in red is average unique risk. Note that that term, average unique risk, is multiplied by 1 over n, and I make that clear here in the next line. So the portfolio error variance is equal to 1 over n times average unique risk. And now comes the big point. Therefore, as n increases, that is, as the number of securities in the portfolio increases, unique risk decreases. This term up here, total unique risk decreases. And since market risk is averaging, total portfolio risk therefore decreases. Since market risk is averaging and unique risk is falling as portfolio size gets bigger, the implication is total portfolio risk decreases as the number of securities in a portfolio increases. That is a very important major point. Thank you for watching this video.